We are continuing, but as is our tradition, let's take a small break and don't be, I don't know, seriously surprised that what has happened to Dr. Zahir. So you see a picture, right? What do you comment? No. You see, Winston Churchill, if you remember, was the Prime Minister of England. And he is one of the most famous Prime Ministers, once because he was the Prime Minister during the Second World War. So under his leadership, England won, right? The Allied forces won. So that is big. But the other thing is that in all their Prime Ministers over several hundred years or whatever, he is one of the most intelligent ones in speaking and making speeches in the parliament and so on. So he used to tell that, you see, when you are making a speech, when you are writing a paper, then how long should you talk? So just listen to this wonderful comment by Winston Churchill, the English Premier. A good speech or presentation should be like a woman's skirt. A good speech or presentation should be like a woman's skirt, long enough to cover the subject and short enough to be very interesting. Joke is over. This is the other type of ABX system, AMBNXP, right? For example, magnesium aluminate, magnesium aluminum 2O4, right? So, right, this time the metal has different, right? This of course is a different number, but even in the metals it is different, right? So aluminum, magnesium, oxygen. So if you see these gray ones, these are all these oxygens. The blue ones are the aluminums, the green ones are the magnesiums, right? So 8 octahedral positions, and this structure is called a spinel structure. A spinel structure. Now I keep on telling you that, you see, in fundamental level course, that this is advanced materials technology of advanced materials. So we are talking of, right, advanced ceramics and advanced alloys and advanced composites and biomaterials and sort of electronic materials. But when we are covering so many different types, then the level of depth that we go cannot be too much. So again, we will introduce you very quickly to advanced, like the spinel structure that you are now doing, the perovskite structure that we did just a couple of slides before. These are now advanced ceramics. But in terms of the calculations and understanding of the atomic packing factor and densities and so on, the examples we have taken from the simple AX type. But the AMX, ABX type, you know it, but the calculations we will leave for some other time. Phase diagrams for ceramic systems. Phase diagrams, right? So ceramics are represented by phase diagrams just like metal alloys. And if you remember, like, the most important alloy is like a ceramic in one way, right? I mean, of course, there is a metal and a non-metal, right? Metal and a non-metal, iron and carbon, but it is metal alloy. Here, if you say silicon carbide, then silicon and carbon make a very different one. So the main thing is that there for a large number from 0.5, 1% carbon all the way to 6+% carbon, the carbon and iron do not form a compound. There are phases of iron, right? and after 6.7%, then the carbon and iron will live completely as iron carbide. So this intermetallic compound iron carbide is in a small quantity and exists like a phase only. Here in ceramics, the metal and the non-metal are completely there as a new compound, not in their individual phases, right? So this is the major difference, that phase diagrams will be here also, but it will not be pure metal phase, pure non-metal phase, and so on. So same principle, but then phase diagrams will be there of a more complicated nature. Same principles for calculation of phase compositions, tie lines, invariant points, solidus, liquidus, solvus lines, all will be there. For example, this magnesium oxide, aluminum oxide phase diagram, right? So on one side you have magnesium oxide, on the other side you have aluminum oxide. Now these are individual compounds already, magnesium oxide, right? And this is aluminum oxide. So these are already individual compounds, and then they together exist. So from 0% aluminum oxide to 100% aluminum oxide, and so on. And then there will be temperature. But because this is already magnesium oxide, so there will be melting temperature for magnesium and melting temperature for oxygen, and so on, right? So it is not one, it is melting. So actually for oxygen you can't say a melting temperature, and so on. Similarly here, that what is the melting temperature for alumina, and in between. So there is the liquid region, right? There is the liquidus line, there is the solidus line, and so on. So if you end up working in a place where these advanced ceramics are being made, then first of all, in any one company, they will be not making 10-20 different types of ceramics. Generally they will be dealing specialized only on 2, 3, 4 types. So very quickly you will learn that, and if this chemistry and all these physics calculations and the materials engineering, then you will become quite good experts in very short time. Here we are just letting you know that this is a complex ceramic and it does have a phase diagram, so we can engineer different types of combinations of this magnesium oxide, aluminum oxide at different percentages of compositions and so forth. What are the industrial uses of ceramics, right? Applications. So very quickly you know, but the American Ceramic Society classifies ceramics into 7 distinct groups: abrasives, glasses, cements, refractories, structural clay products, whitewares, advanced ceramics. And each group possesses distinct properties and challenges, right? So these are all ceramics, and each one of them is a very different application and a different market. So we have taxonomy of ceramics: glasses, optical composite reinforced containers, clay products, refractories, high temperature resistant, abrasives for cutting and grinding wheels, cements, and advanced ceramics. Advanced ceramics in engine rotors, in valves, in bearings, in some sensors. So these are some of the latest ones, but in abrasives and others also there are many new developments being made. Abrasives, you know, wear away other materials through processes like sanding, grinding, lapping, pressure blasting. Abrasive particle acts as a cutting instrument, ripping away parts of the softer material, you know, grinding wheels and grinding machines. Hardness is the most important property in an abrasive. Friable materials, you can fry them. Friable materials form fragments with sharp edges when they break under stress from heat and pressure, right? So abrasives are already very hard and sharp, but if they belong to the friable category, then they make small particles which are even sharper. So you apply a stress, they break, but they break into still good abrasives, right? Sandpaper, you know, you have been using sandpaper from your first machine shop, workshop practice, and so on. So most familiar abrasive product with hard particles bonded to a backing by a resin, right? Like on paper or something. Earliest sandpaper paper dates back to 13th century, right? So almost 900 years ago, China, where seashell fragments were bonded with natural gums to shark skins or parchments. So they were using natural skins, natural leather and so on, and seashell. They will grind the seashell and then glue it, and then they will use that as a sandpaper. First US patent for sandpaper was in 1834. Pieces of glass were attached to paper, so the name sandpaper. Modern sandpaper has evolved beyond glass. Some no longer use paper but mylar, cotton or rayon fabrics as a backing material. They are classified based on the grit size, which means number of abrasive particles per square inch. So grit size, right? When there is a smaller number of grit size, it means that the particles are larger. So the number of particles per square inch is small. So 40 to 60 is coarse, 80 to 20 is medium, fine, very fine, extra fine, super fine. And uses these small ones, stripping or large scale sanding, smoothing, final wood sanding, and mark removal of surface scratches. So these are different categories of sandpaper, right? Sand, right? Glass, any other material which has been broken down into very fine and sharp grains using some resin or some glue. They are bonded to paper or different types of paper or different types of cloths and so on. Abrasives used in sandpaper. 4 distinct types of abrasives are used in the sandpaper: alumina, garnet, silicon carbide, and something called a ceramic. They are all ceramics, but this is itself called a ceramic. And each material is used for different tasks. So the type of abrasives, right, the sharp particles that are there in the sandpaper belong to these 4 categories. Alumina, right? So we know this. We have done this earlier. Aluminum oxide. Aluminum is the metal, oxygen is the non-metal, right? It is a face-centered type here, and there are the other. So this is there, right? Most common abrasive. It is friable. When you heat it and pressurize it, it breaks into smaller pieces. It has good toughness. It has good hardness. It has this density. It is insoluble in water. It has a very high melting point. Of course, it is a ceramic, and it is very common, inexpensive, because alumina is a very common material. Now, alumina forms corundum structure. This structure is called corundum structure, which is very different, right? This is not hexagon. This is not cubic. This is not cubic, right? This is hexagonal. This is hexagonal, right? So the top face, the bottom face, and in the middle. So this is hexagonal close packed. So this is hexagonal close packed structure. Exceptional hardness. Many gemstones are alumina with specific impurities. Chromium can be added to alumina, then it becomes rubies. Iron and titanium are added to alumina and it becomes sapphire. So this is big, right? That simple alumina is very low cost and so on. But naturally, if some chromium or some iron and so on are added to alumina, then you get very special gemstones like rubies and sapphires. So of course, you don't use rubies and sapphires as general abrasive materials unless you have some very high quality abrasive to be used. Otherwise, a standard alumina, which has this corundum type of HCP structure. Garnet, you already know, is a semi-precious type of material. A variety of materials with A3, B2 silicate type of structure. So the A and B could be anything, but this is silicate, right? Aluminum garnets, chromium garnets, iron garnets, depending upon identity of this material. Softer than alumina, not friable, less suitable for removal of large amounts of materials, but is still good enough for sandpaper. Sharp edges are smooth out during sanding, so the sharp edges are gone after some work, but used on soft woods and for final finishing, right? For final finishing and for soft woods rather than for main scale abrasion like in a standard grinding machine and so on.